So this is level 4 of power distribution network analysis, and it is a kind of mixture of whatever we have discussed on all the 3 levels, and we're going to sum up with a really complex power distribution network analysis. And yeah, before starting and before going for power budget, let's discuss the schematic and its layout. So this is our layout, and you can see it's kind of a lot of chips are there. There we have the same motor driver that we have used on level 3, and but yeah, MOSFET is changed, which is basically driving the motor. And here we are using some couple of digital chips, and a lot of input signals are there through these 3 16-pin connector, and the couple of analog inputs are also there, which is through these potentiometers. So there are lot of things that we're going to discuss. Now we'll start from supply. So this is our supply, and I haven't mentioned what will be the voltage here because that will define through power distribution network analysis. Yeah, but it is going to 2 regulators, which is 7805 and 1117. From there it is going to this motor driver, and again it can able to drive 3.5 amps of motor. That is again a kind of fixed amount of current. Yeah, and then we have some analog buffers which is connected to 3 potentiometers, and then we'll have lot of digital interrupts. So here we have connected 8 switches on this MUX, right? And each switch has its own load, which is this LED and 1 kilo ohm resistor, and but it has debouncing circuit as well. So this is something we are going to calculate the amount of current, because all these digital chips will be 1 microamp or few microamp load current. So we'll kind of not consider them, but still we'll go through their data sheet. Another is this shift register and MUX logic level converters. So here again we have some inputs which is connected to some buffers, and from buffers it is going to logic level converter, and from logic level converter it is going to MUX, and which is again connected to some microcontrollers or something. But here the major load will be these pull-ups, because when we'll have logic level 0 here, the amount of current will flow through these pull-ups, and it will sync through these this buffer and connect it to ground, right? So there we have to calculate the amount of current flow, and that will be our major load on these particular signals, because these IC will be again like some microamps or 0.1 microamps low amount of current. So yeah, this is the complete circuit. Let's design our block diagram and power budget.
People who don't know which tool I'm using, it is Altium Designer 22.1, and if you wanted to get the free trial of that tool, I put link in the description. You have to just click there and register yourself. Within 24 hours you'll get the license. PDN Analyzer tool is a separate license from Altium Designer. So for that I have put a separate link. For purchasing PDN tool license, you have to click over that link. With that said, let's roll the intro.
So for that we'll start from DC jack, right? So firstly here we'll have 3 circuit blocks. We'll start with circuit block 1. For block 1 we'll start from DC jack. Alright, which has a particular net, I've told you, VM, right? Now it is connected to 2 regulators or LDOs, which is 7805, which will give us plus 5 volt, and 1117, which will give us plus 3.3 volt. Now this VM is further connected to motor driver. So here we'll mention, like we did before, DRV plus MOSFET, right? And here major losses will be through MOSFET because it will have its own RDS on, and we have huge amount of current, which is 3.5 amps. So this is our MOSFET, and our load here, we know the amount of load, which is 3.5 amps connected on this one. Okay, so this is our circuit block 1. And about these current, so here we know the amount of current, we have to just take care of losses here, but here we don't know what amount of current is flowing through this one, right? And from datasheet we can able to see what is the voltage drop across these, and accordingly we'll see what amount of VM should require here. Alright, so let's move to another circuit block. Okay, now I can scroll down. Okay, so let's move to block 2. For block 2, I'm going to consider 3v3 input. Okay, and I'll just keep explaining you one by one. So the first 3v3 input is going to analog buffers. Okay, I'll show you where it is. Okay, so this is analog buffer chip or IC. Okay, and its amount of current is 1 microamp. It's 1 microamp. Is really small, so we'll not consider that, but still I'll show you where it is. So it's here. Sorry, this is the analog buffer, so you can just double click and copy this manufacturer part number, and you can visit its data sheet. But major amount of current is flowing through this one. So I know this is basically, these are potentiometer which is further connected to some actuators, and when that actuator is rotating, we need to get a particular location. So these are the potentiometer where we are measuring the degree, like how much degree rotation already happened through those actuators, right? So here we are not using any tachometer or something like that. So this is something some cheaper version of rotation measurement that we are doing here. But yeah, I know it should stop approx. So these are 10K potentiometer and should stop at 1K, and that is what I want. So maximum amount of current will be flowing through these one will be 3.3 milliamps multiplied by 3, right? So that is again a kind of load that we have to mention here. So this is 3 potentiometers and 1 kilo ohm. Okay, so it will be 3 into 3.3, which will be 9.9 milliamps. Okay, or approximately 10 milliamps will be flowing through these potentiometers. Okay, that is a kind of load on 3v3. Another load will be through toggle switches. So I'll mention here first, then we'll see where it is. So we are using 8 toggle switches, and those will be again connected parallelly through 3v3, and the amount of current on this one will be 8 into 3.3 milliamps. Let's do that calculation as well. I'll show you where it is. So it is 8 into 3.3, which is 26.4 milliamps. 26.4 milliamps. All right. Let's see where are these toggle switches. So we are going to connect toggle switches on these connectors, right? And when we press the switch, this M1 underscore ext underscore u will be connected to ground, right? And where it is, where this M1 is there, it's there, right? So when this will be connected to ground, the amount of current will flow from here to here. You're getting it? Because this will be 10K, right? And here this diode is connected in reverse bias. So this amount of current will be continuously flowing until the switch is pushed, right? So we have 1K resistor in series, and this LED will obviously glow. So what is the amount of current will flow through this one? That will be 3.3 milliamps, right? So that's why I multiplied it by 8. Similarly, we have muxes. So if you'll check the, I'll go back there. So on this, we have couple of more chips. I'm just going to mention here. So we have one 8:1 mux. All right. We have logic level converter. On A side, we have connected this 3v3. So A side logic level, and we have another mux which is dual 4:1 mux. Okay, and these all current are in some 1.1 microamps, right? So I've already measured that. If you want, you can also go through the other data sheet. So what is the total amount of current flowing through this 3.3 volt chip? It will be 10 milliamps. This one will be 36.4 milliamps, and these are microamps. So we'll ignore that, which is 36.4 milliamps, right? This is the amount of current which is flowing through 3v3. Now let's move to 5 volt supply. All right. So similarly, on plus 5 volt, you'll see a couple of chips, but here we have buffers which is connected to 8 10 kilo ohm resistors, right? And it is connected to 5 volt. That means 8 into 0.5 milliamps. Let's see what amount of current it will be. 8 into 0.5 will be 4 milliamps, right? Okay, so this will be total 4 milliamps here. Another load we'll consider. Okay, so here two ICs are connected, which is U1 and U3. You can check it out. U1 plus U3. Okay, these are again a buffer, so their load current is 2 microamps for 2 chips. Another is we have okay, so here we're going to connect some U4. Okay, let's see what U4 is. Okay, so we have one level converter, and that is again some microamps, 1.1 microamps or something. So this is our level converter, and B side of the level converter is connected to 5 volt. That will be again some 0.1 microamp, right? So again we'll ignore this thing, which is approximately 0. For this one, we'll see from here we have 4 milliamps of load, right? Now let's go back to our first block, which is this one. So here we'll mention the amount of current. For this one we have 4 milliamps. For this one we have 36.4 milliamps. For this we have 3.5 amps. Here we'll see what is the voltage drop across these three, and accordingly we'll calculate VM. So for 7805 we know the voltage drop is 2 volt. For 1117 we'll see. So I would go back to our power supply page. This one, copy this part number, open Chrome. Let's open data sheet of this thing, and we'll see voltage drop. So it's 1 volt typical. Okay, so we'll see it is 1 volt, right? Then for MOSFET, we'll again open the data sheet of MOSFETs. So this is not 4 channel MOSFET, it's dual and N channel MOSFET, and its RDS on is 4.7 milliohm. But again, you know, we are using those as a H bridge. So 7.4 multiplied by 2 will be approximately 15, right? 15 milliohm. So we'll open that, and here the resistance will be 15 milliohm approx. Now the voltage drop across this will be, let's open calculator. So it is 15 multiplied by 3.5, which is 52. So voltage drop will be 0.52, right? So here the voltage drop will be 0.52 volt, and here the voltage drop will be 1 volt. And so let's add all these together. So it will be 3.52. So that means this voltage will be 12 plus 3.52, right, which is approximately 15.5 volt. This is the amount of voltage we need here, right? So yeah, this is the power budget of our level 4, and let's put all this information on PDN tool and see where our circuit is failing from board point of view.